ISHRAE, Indian Society of Heating, Refrigerating and Air Conditioning Engineers. Founded in 1981 at New Delhi by a group of eminent HVAC and R professionals, ISHRAE now has a total of 41 chapters and sub-chapters.
ISHRAE gives you the latest industry insights of the HVAC and R and building industry and delivers latest technologies in forms of technical blogs, videos, and articles to people. It has more than 14,000 members and about more than 10,000 student members. ISHRAE releases various standards for HVAC and R building industry time to time. It organizes more than 800 events every year, including seminars, conferences, product presentation and more. ISHRAE also provides handbooks and guidelines. ISHRAE also has student chapters in more than 150 engineering colleges, to encourage students, and let them know about HVAC and R industry. Visit now, ishrae.in, for more details.
Hello, good evening all. Hello, good evening and welcome to all. Myself is Ravi Kumar. I am from ISHRAE headquarters. So I am the coordinator for the webinar series on refrigerations. So I am inviting Mr. Anish Sima, who is the chair of the refrigeration committee. Mr. Anish sir, over to you.
Yeah. Can I have the screen, please? Is it visible, Ravi?
It's visible to all.
Yeah. So, good evening, all of you, for the second webinar of the 7 power pack session by one of the most experienced professional of the industry, Shri Ramesh Paranjpey. Today's webinar is on advantages and drawback of ammonia as refrigerant. You can see the lot of advantages of ammonia as the refrigerant. Okay, I would like to introduce Mr. Ramesh Paranjpey. He is the fellow life member of ISHRAE. This year, Shri Paranjpey has been awarded the 50 years Distinguished Service Award from ISHRAE. He is the member of the ISHRAE Fundamentals 2017 Volume Committee. He is a member of IAR USA, and he has the MTech from IIT Mumbai or IIT Bombay earlier. Professionally, he has worked 6 years as the Chief Executive Officer Voltas Air International Limited in Pune. Before that, he was the Managing Director of Carrier Refrigeration Limited, worked both in Bangalore and at Singapore. Prior to that, he had a 27 years work experience with Kirloskar Pneumatics Pune, where he also reached the Vice President position at Kirloskar Pneumatics in Pune. Okay, one second. Yeah. Mr. Ramesh Paranjpey was he was the examiner, and he used to set papers for the University of Pune for Master of Engineering, and also formulating he was in the syllabus formulating committee. He has published more than 45 papers in international and national journals, conducted more than 300 training programs at Honeywell, Alpha Level, Voltas, Blue Star, Thermax, Emerson, Tata Motors, LG, ISHRAE and ASHRAE forums, and on international level in the US, Singapore, China, Germany, etc. So, reason for getting the ASHRAE fellowship is meeting ASHRAE objectives in sharing knowledge and information through publishing papers and conducting training programs, as well as promoting the arts and science of refrigeration and air conditioning. Sri Paranjpey has achievements. He was invited by the German Chamber of Commerce to deliver lecture in Germany on ammonia pump circulation systems for low temperature applications. He has presented a paper in IIR conference in Macedonia on energy saving techniques in ammonia pump circulation systems. He has been the winner of the Breyer Systems Design Award and winner of the Lifetime Engineering Award organized by ICE Danfoss or Global Cold Chain in 2012. He has published a book on cold room solutions for Emerson climate technologies. His published book for Danfoss controls, how to use ammonia, making it easy and safe to be efficient. He has published a book on air cooled design for cold storage for Alpha Level, and he has executed more than 700 projects for cold storages, including the ice cream making, process plants, fish and meat freezing, as well as air conditioning, such as international airports, office buildings, and shopping malls. And you can contact our guest speaker today, Sri Paranjpey ji. The details are here. I would now request Ravi to share the screen with our speaker, Sri Paranjpey ji.
Yes, sir. I have already given the rights to Paranjpey, sir.
Okay. You are able to see the screen or show my screen? I'll click on the show my screen.
Sir, you need to click on that. Show my screen.
Oh, now you can see the screen?
Yes, yes, yes. Now we can see your screen.
Okay. So can I go ahead now with my presentation?
Yes, yes, sure.
Okay. Good evening to all of you, those who are attending the seminar. And I'm once again, thank you, ISHRAE headquarters and the committee for giving me this opportunity. I also want to thank all the people who attended the first program and gave me overwhelming good appreciation. I have received so many mails and so many letters that I am very thankful to all the people who have attended it. That increases my responsibility because every seminar or every portion which I am going to show has to be better than the earlier one. Anyway, let us start now this session. And the next slide, this is the first slide. The next slide is going to be what we will recollect what we discussed in our first session. In the first session, my stress was mainly to show that the global warming is a major issue. CFC, that is ODP issue, is over, but global warming is now greatest issue. And two things we need to do as refrigeration air conditioning engineers. That is, we must use refrigerants which are low global warming refrigerants. And global warming is out of two reasons. One is, of course, leakage of refrigerant, but I showed that 90% contribution is because of the energy consumption. So the refrigerant should be low global warming and also should be very highly efficient. This was the two major issues with which we discussed in last seminar. Then we discussed briefly that ammonia is the most efficient refrigerant and it has practically no global warming impact. Now today we are going to discuss all the good and the bad points related to ammonia refrigerant in more details. This slide, if you remember, is a repetition what I showed last time, but I am showing it again to show you that these are the refrigerants: SO2, ammonia, CFCs, HCFCs, hydrocarbons, etc., and carbon dioxide. Out of all these, every line is a break line, whereas ammonia line is a continuous line, indicates that right from 1875 till date, it is continuing being used in the fields where ammonia is most advantageous. Now let us look at the history of ammonia as a refrigerant, how ammonia was introduced in so early years. So ammonia was first used as a refrigerant in 1850s, and that was in France, and it was applied in United States in 1860s for artificial ice production, The first patent for ammonia refrigeration was filed in 1870. And 1876, Carl Linde used ammonia absorption cycle for the domestic refrigerator. So this is the cycle shown. There is a heater or a burner and there is an absorber. And ammonia is used as a releaser or vapor. Absorber was water. So this is the photograph of the household refrigerator using absorption technology in the year 1880, using ammonia as a refrigerant, which was circulated in the coils, in the condenser and other places. The next slide shows an original block ice machine in 1879. Now, if you can, the most important point to be noted is look at the ammonia compressor and the electric motor. You will find that electric motor, sorry, I'm going back to the electric motor was not invented at that time, so it is driven by the steam engine. If you see, there is a steam engine which is driving the compressor, and on the right hand side there is a block ice machine. The next slide shows Linde's first ammonia reciprocating compressor, which he constructed in 1876. The first compressor was installed in a brewery for making beer in Triste and exhibited in Paris exhibition in 1878. So this is the brief history of ammonia as a refrigerant. And refrigerant, now when we talk about refrigerant, we must understand what is the function of a refrigerant in an entire system. Now, what happens when we design a system and install it? The system is mounted in a machine room and air coolers in the cold room, evaporative condenser on the terrace or elsewhere, and all these are stationary items. And the function of the refrigerant is a heat mover. It is a heat mover. What we want to achieve is cooling. So from a place where there is heat to be removed, some agent should take that heat into it and reject it where it is unwanted. So that function is done by the refrigerant. Refrigerant is operating like a heat pump. It picks up the heat where it is not required and whether it throws it out into ambient where it is not objectionable. So that is the function of a refrigerant. So refrigerant travels inside the circuit and does this function, whereas all other components are stationary. So this is just to give a very general comparison. It is like a bus, our corporation bus. It picks up the passengers at a particular depot and passengers travel. The bus drops the passenger at a destination and again bus comes back to pick up the additional passengers. So it is just to give a similarity so that you will remember what is the function of a refrigerant into a system. Now, why do we recirculate the refrigerant? Because refrigerant, we don't want to waste it. Otherwise, you can use refrigerant and throw it to atmosphere. For example, if you use nitrogen as a refrigerant, you have to, it is not recoverable. It is to be thrown out to atmosphere every time. So, but our other refrigerants, CFCs, HCFCs, ammonia, natural refrigerants, hydrocarbons, we cannot afford to waste them and we have to recirculate them. So therefore it is a closed circuit. Now look at the evaluation process of refrigerant. First we talk environmental impact. It should have no global warming, no other adverse effect on the environment. The performance, second is COP. We discussed COP, which is a dimensionless quantity, which is output in kilowatt and input in kilowatt, both in kilowatt units. Or a lot of people are used to, those are old timers, they used to remember TR, tons of refrigeration. So energy efficiency used to be called as kW per TR, kilowatt power consumption per TR. That is also one of the yardsticks. The next is toxicity and safety of the refrigerant and human beings. The next point is flammability. The refrigerant should be non-flammable as far as possible. Then material compatibility, whatever material we are using for compressors, electric motors, piping, valves, controls, the refrigerant should be compatible with it. The stability of the refrigerant should not disintegrate during operation, so it has to be stable. And finally, the cost. The refrigerant should not cost too much. It should be affordable. So these are the general properties of a refrigerant. But now we see at the thermal or physical properties of this refrigerant. What are the thermal and physical properties? The boiling point, the most important point is boiling point. The boiling point should be lower than the operating condition. For example, if you are operating the plant at minus 10 degrees centigrade, the boiling point of the refrigerant has to be lower than minus 10 degrees centigrade. Then only refrigerant will remain in a liquid state in the evaporator. If the boiling point is higher, it will be in the vapor state. So boiling point should be lower. The next point is discharge temperature. Now the discharge temperature of the gas coming out of the compressor should be in the range of 130 to 140 degrees centigrade maximum. Why it is so? Because our mineral oils, what we use in our refrigeration plants, are capable of withstanding up to these temperatures, after which they start disintegrating. Nothing happens to compressor parts. They are cast iron, they are steel, and which can withstand very high temperature. But because of the limitation of uh, oil, we limit it to around 130 degrees centigrade, and also from the efficiency point of view. The next point is discharge pressure. The discharge pressure of the compressor should be manageable, or a system. Condenser pressure, compressor discharge pressure should be manageable. For example, ammonia operates around 12, 13, 14 kg maximum pressure. Whereas if you go to carbon dioxide, it will be 60 to 70 kg per centimeter square. So all your components have to be designed to withstand that pressure. All our other refrigerants are between 10 to 14 kg per centimeter square pressure. The next point is specific volume. The specific volume should be low so that your size of the compressor, size of other equipment becomes smaller. The density, the next point is density. We will deal all these in more details in our subsequent slides, but this is just the summary. The density should be as high as possible. So your mass flow rate will be then substantially lower. The next is latent heat of vaporization. This is a very important property, the most important property. It should be as high as possible, because it is the latent heat which makes refrigeration work, both in condenser, when we call condenser, and evaporator. Evaporator, the refrigerant evaporates, so it is a latent heat transfer process, and in condenser it is condensing, so again gas gets converted into a liquid for reusing it. So latent heat is very, very important, and the compressor displacement should be as small as possible, so your size of the compressor becomes small. For example, just to give you an example, carbon dioxide. The carbon dioxide compressor is so small, last time I had mentioned, it is nearly 1/7 size of the other refrigerants. So it's a very compact uh, compressor. Now let's go into ammonia. Ammonia R717 7 series is a natural refrigerant which we discussed. 17 is a molecular weight, that is NH3, 3 hydrogen atoms and 1 nitrogen atom. So 14 plus 3 is 17. So 717, all natural refrigerants show first digit as 7 and next two digits as molecular weight. Now let's look at ammonia as a natural refrigerant, and why it is natural, because it is produced in nature by way of human beings, animals, etc. Every human beings, you will be surprised to know that we produce 17 grams of ammonia per day. So this is our production of ammonia, contribution of ammonia. The natural production is 3,000 million tons per year. Production in factories is 120 million tons per year, but we use hardly 0.2% of it in refrigeration, which is around 6 million tons per year. So this is the total ammonia in the world available. So you can see how safe it is compared to all other refrigerants. Now, ammonia, when we select ammonia, we need to take care of certain properties of ammonia. For example, in fertilizer grade, when we use 95% ammonia as a fertilizer, the ammonia content the purity content is 99.5% only. But when we use as a refrigerant, it should have a minimum purity of 99.95%. So it is much purified refrigerant, when we use into the system. We cannot use fertilizer grade ammonia into refrigeration plant. Now, if you look at the color of the ammonia in a test tube or something, its appearance is more or less colorless. And now, if you smell, everyone knows that ammonia has a smell. It has a typical characteristic pungent smell, irritating pungent smell. The other important environmental properties which we looked at: ODP, ozone depleting potential 0, global warming potential 0, atmospheric life nearly 0. It disintegrates into ammonia and hydrogen if it leaks. And the water content, we have to limit it to around 33 ppm maximum. Oil content 2 ppm. Non-condensables 0.2 milligrams per gram. Salt content nil. Pyridine, hydrodyne, naphthalene, etc. nil. Molecular weight, as we know, is 17.031 to be precise. And concentration in human blood 0.8 to 1.7 ppm. Now, these are all figures. You need not remember all these. Only remember that it has to be 99.95% pure. Don't use any fertilizer grade of ammonia into refrigeration system. The next, this slide is important because it gives all refrigerant grade properties. The boiling point, as I mentioned, at boiling point is always, remember, when we say boiling point, it is always at atmospheric pressure. So at atmospheric pressure, which is 101.325 kilopascals, is minus 33.33 degrees centigrade. So up to minus 33 degrees centigrade, you can use ammonia where the system pressure will be positive. But if you use for blast freezer minus 40 degrees centigrade, you will find invariably the pressure is negative. The plant works under vacuum, little bit of vacuum. The freezing point or a triple point is minus 77.66, which is very low. Triple point is a point where all three phases exist together. That is solid, liquid, and gas. That is the definition of a triple point. The critical temperature is very, very important. And look, just remember this figure. Critical temperature of ammonia is 132.22 degrees centigrade, which is the highest amongst all other refrigerants. Another very important point to remember is relative density of vapor. The density is 0.596 compared, so it is lighter than air. Air density is higher. The molecular weight of air is 29.86, whereas molecular weight of ammonia is 17. So ammonia is much lighter than the air. Whereas all other refrigerants, man-made refrigerants, even the hydrocarbons, all of them are heavier than air. Then this is a bad quality of ammonia, which we will discuss later on. People always talk, those who are against ammonia or those who are not manufacturing ammonia equipment, they will try to promote HFCs, HCFCs, and they will say, oh, ammonia is flammable, ammonia is toxic, etc., etc., etc. But if we have an open mind where we use both ammonia and other refrigerants, then we will discuss this further. As you know, if you wear green specs, everything looks green. So we have to be careful in talking about, when we talk about properties of ammonia, which are good properties and where we need to take care of it. The ignition temperature of ammonia. People talk that ammonia is flammable. Now look at the ignition temperature of ammonia. It is 651 degrees centigrade. Nowhere in our refrigeration system we reach these temperatures. The next important property is specific heat ratio, that is gamma, index of compression, what we call Cp upon Cv, that is specific heat at constant pressure, specific heat at constant volume. This ratio for ammonia is 1.32. What is the significance of this? We will discuss in our further slides. The solubility of water, as you can see, 0.571 kg in 1 kg or 650 grams in 1 liter of water. So ammonia is very soluble in water and it is known as aqua ammonia solution. We will talk about this property also in subsequent slides. As we discussed, look at this photograph which shows what is all the ammonia in the nature. 100,000 lakhs tons, 1,000 lakh tons in produced by a man and hardly use 3 to 5,000 tons by refrigeration industry. And so advantages of ammonia as a refrigerant, now one by one we will start discussing. The first slide shows, last time we showed a slide on global warming. Now I'm showing you a slide on ozone depletion potential. Ozone depletion potential is always measured in terms of R11 refrigerant. R11 refrigerant is taken as 1. Now R11 and R12 both are not available now, but when they were available, they became a yardstick for measurement of all ODP values. R22 has 0.05 ODP. We still continue to use R22. We are, as a developing country, allowed up to a particular limit, but now no one practically uses it. The ammonia, the arrow shows 0 ODP. So 134A, 404A, 407C, 410A, whatever we are using today, all have 0 ODP. The next slide is global warming. Now, as we discussed, ozone depletion is in terms of in one as a yardstick of R11. Here the yardstick is carbon dioxide. We saw in global warming carbon dioxide effect, and compared to 1 kg of release of carbon dioxide, if you release 1 kg of R12, it is equivalent to releasing 8,100 kgs of carbon dioxide. Or in terms of, let us forget about R11, the 404A we continue to use. It has a large global warming, 3,260. So 3,260 kgs of ammonia, CO2 we are releasing if there is a leak in 404A system and 1 kg of refrigerant leaks. R410A also is 1730 and 407C 1530, R134A is 1300. So all these refrigerants what we are using, right from 1300 to 3200 kg of release of carbon dioxide, all are contributing to huge global warming, and therefore last time we discussed that these refrigerants are to be now phased out. As per the Kigali agreement, these have to be phased out. Now if you see the last ammonia has a 0 global warming potential. So ODP is 0, global warming is 0, and the last slide is atmospheric life is also very, very important, because if the refrigerant is stable in atmosphere, because of the Earth's rotation, it rises in the troposphere and then damages the environment. Whereas ammonia has a 0 atmospheric life. As soon as ammonia leaks, it breaks down into its components. That is nitrogen and hydrogen. Both are naturals and they are not at all harmful. They are available in nature. So this is atmospheric life is a third property. So ODP 0 GWP 0 and atmospheric life is 0. So these are the three very important properties of ammonia. Now this is a summary slide. I will not repeat these figures again, but I have added, because in earlier slides these refrigerants were absent, like propane R32, R1234ZE, R1234YF, etc. These are now new refrigerants the world is trying to introduce. Now these refrigerants have atmospheric life 0 because they are the mixtures and they disintegrate, but their GWP is 6,4, substantially lower compared to all these other refrigerants. The propane is a hydrocarbon, 3.3 GWP and 0 atmospheric life. So these are the summary slides of all current, old and new refrigerants. What is now, we briefly touched upon TEVI, and I got a lot of mails based on our last presentation that please explain TEVI in little more details in your next presentation. So TEVI is total equivalent warming impact and takes into account total related emissions of the gases, both direct emissions and indirect emissions, that is leakage of refrigerant and energy contribution. So CO2 content and is measured in terms of carbon dioxide. So TEVI is calculated as a sum of two parts, that is refrigerant released during the lifetime of the equipment, including uncovered losses on final disposal. That is, when you destroy the equipment, some refrigerant which is inside the equipment will be released to atmosphere. So it takes into account that impact. Also, it takes into account the impact of equipment's lifetime power consumption figure. Okay, so it is an addition of both of these. There is a formula to calculate TEVI. It is defined as a sum, as I told you, and the formula is GWP into L into N plus EA into beta into N. What are these? L is the annual leakage rate of a system, which is considered as 3% of a refrigerant charge annually. N is considered as life of the system. Let us take 15 years life of a refrigeration system. Then you need to be discarding it or upgrading it. The system running time per year is taken as 4,910 hours. This is based on a general refrigeration uses, including air conditioning and refrigeration. EA is the energy consumption kilowatt per hour for each refrigerant. Beta is carbon dioxide emission factor, and CO2 is equivalent emission in kilowatt hour. That is 165 grams of CO2 assumed as per kilowatt hour is released. So this is a TEVI formula. You can calculate for any refrigerant. You can vary these figures, whatever have been mentioned. This is the TEVI slide, total warming impact, ISHRAE journal 2013. It is a combination of various systems. Indirect effect is shown in light color, recycling and direct effect is shown in dark color. Now, what are the systems? Medium temperature and low temperature. 404A direct expansion, 404A direct expansion for low stage, 404A carbon dioxide cascade system, 134A CO2 cascade system, 404A, which is current refrigerant people use as a chiller with propylene glycol or CO2 as a low temperature secondary fluid. Propane chiller pumped CO2 as a secondary fluid. Ammonia chiller pumped CO2 as a secondary fluid, 134A CO2, and transcritical CO2 and CO2, both high stage as well as low stage. Now, these are the total equivalent warming impacts, and I have shown in green arrow that out of all these, if you see, ammonia is 2577, which is the lowest. The second is 2587, that is propane, and third is CO2, which is 2661. All other refrigerants, whatever combinations you use, they have a very high TEV effect. This is a calculation done on the basis of 35 degrees centigrade condensing and minus 20 degrees evaporating temperature, R22, 134A, 407C, 410A, and ammonia. If you see the TEV effect, that is kgs of CO2, 29,07,800 for R22, 28,56,134A. R410A is the highest, 31,70,407C, 30,82,000 for 410A. And look at ammonia, it is the least, nearly half of all these, 14,57,000, because if you look at the first two figures, operating leakage, carbon dioxide is 0, fluid recovery is 0. It is only the energy whatever refrigeration plant will consume in the formula, that is the only effect with ammonia. I trust I am very clear now on TEV, and this is a slide again which shows comparison at various evaporating temperatures with various combinations. We'll not go into more details because we have to discuss a lot of other properties. This is a further development. I'll just show the slide. LCCP, that is life cycle climate performance. This is a new terminology. People have still all calculating this. So it takes into account TEV plus GWP of energy consumption for chemical production, that is refrigerant production, transportation of refrigerant, manufacturing components and assembly cost and end of life. And GWP, global warming, that is emission including atmospheric reaction of products, manufacturing leakages and end of life. This is a little complicated terminology, still it is not very popular and people are calculating LCCP values. But as a slide, I just wanted to show you. Now I did mention that importance of latent heat of evaporation. It is the latent heat which makes refrigerant work because the phase change takes place. Liquid gets converted into vapor, and in condenser, vapor gets converted into liquid. Sensibly, it does not do any cooling effect. A lot of people say that, oh, the condenser has to be designed much bigger because discharge temperature of refrigerant is high. That is only sensible heat. It is hardly 10% or 15%. 80% area of the condenser is used for latent heat transfer, that is condensing of refrigerant. For example, at minus 10 degrees centigrade, enthalpy of ammonia liquid is 1450.70, whereas specific heat, that is heat required to raise the temperature, sensible heat, is only 4.5. That is nearly 370 times, 320 times more energy is required for latent heat. And therefore, latent heat is important because it absorbs a lot of heat when it is evaporating into the evaporator. The latent heat comparison of these refrigerants. Water has the highest latent heat when used as a refrigerant. There are some instances of water, but very large plants, not our regular refrigeration plants. Ammonia, 1247.85. And if you look at other three refrigerants which we are currently using, 410A, 134A, and 404A all have extremely low latent heat. That is nearly 6 to 9 times lower than ammonia. So you can see how efficient is ammonia refrigerant compared to 410A, 404A, 134A, other things. Now those who are selling these refrigerants and their systems, they will never talk about it because it is a negative point for them. They will talk only ammonia, flammability and toxicity. So we must have a balanced view and see all the properties. This is a latent heat comparison. Again, chart shows water, ammonia, propane, etc., etc. Now, energy efficiency. As I told you, it is a dimensionless quantity, or in layman's language, if you ask, what you get and what you spend, what you achieve and what you are spending. So it is a ratio of that. Now this is an ISHRAE chart, fundamentals table, which shows COP, coefficient of performance of all refrigerants, starting from ethane, carbon dioxide, propylene, propane, and the current refrigerants also, R32, R134A, etc., etc., etc. And you will find that I have marked green arrow. If you see coefficient of performances of all these refrigerants except R12, which is now no longer available, all other refrigerants have lower COP than ammonia. R11 is also 502, but it is no longer available. It is banned because of ODP. So available current refrigerants, ammonia is the best refrigerant available. Okay, 113, the last refrigerant is also banned. Now, this is a slide not available with ISHRAE because ISHRAE always compares with 35 degrees condensing or 30 degrees condensing. In India, we have 40 degrees condensing, which is very common. So this is the slides prepared by me, capacity, power consumption, and COP. If you see, I will not read all the figures, but again, if you see, for this is chilled water application, that is positive temperature applications, ammonia has 6.2 COP, whereas all other refrigerants have a lower COP than ammonia. These all slides are going to be available to you on net. ISHRAE will provide you all this data, and as I did in last time, I'll prepare a Word document and I will also send all these slides to you. The next is your cold storages, which is around 2 positive temperature cold storages, fruits, vegetables. So you work around 0 degrees, -1 degrees, -2 degrees. So I've taken -5 degrees, 40 and -5 degrees. Again, you will see that ammonia has the highest COP amongst all refrigerants. The arrow will show you that. The third slide shows cold storages, that is frozen cold storages, ice cream, meat, fish, etc. And you will find that the COP is again highest for this also. So ammonia is very widely used for all these frozen applications. Lot of people are currently saying that no, it is a populated, thickly populated area like Calcutta or Bombay, Nehru, and they want to use R 410A, 47, 404A, etc. But they are less efficient. They will contribute to global warming. The last is freezing application. If you see blast freezers, plate freezers, the ammonia again contributes as a high SCOP. So all these 4 applications we have taken: positive temperature, fruit preservation, vegetable preservation, low temperature preservation, and blast freezers. All these, this is a summation slide. You will find ammonia scores over all other refrigerants in terms of efficiency. Okay, now let us see the performance of compressor, reciprocating compressor. I will not name the model of the compressor because it is not good to talk about any manufacturer, but I have taken these figures from a compressor manufacturer. Ammonia has, if you take COP and if you take 1 over COP, that is the energy efficiency ratio as 100, R22 consumes 120, 20% more power. 134A consumes 28% more power. 404A 41.9%, and 507 consumes 43% more power. So ammonia consumes in reciprocating compressors also, compared to other compressors, the least power. Lot of people will say that screw compressor consumes lower power. Let us look at screw compressor. This is one of the screw compressor manufacturers' ratings. Ammonia, the COP is 1.912, and I have taken this yardstick as 100%. R22 consumes 98.6%, but it is getting banned now. The 134A, 404A, 507, and 410A, all of them consume 120%, for 24%, 23% higher power compared to ammonia refrigeration in screw compressors as well. Now, another important property is density. Let us talk about density of refrigerant. I mentioned to you density is important. Ammonia is lighter than air. It's only 17.2 molecular weight. Air is 28.96. Propane 44. 410A 72. 404A 72. 2286. 134A. So all you see, all these are higher, heavier than air. So from the above table, you will see that ammonia is the only lighter. Now, what is the advantage? You will ask me, okay, ammonia is lighter than air, but what is the advantage? So let us see what is the advantage. If machine room is not ventilated and if ammonia leaks, ammonia will rise in the air, where all other refrigerants will settle in the machine room. And what will happen? Gradually, the level of this refrigerant leakage goes on building because they are non-smellable, and they will displace the oxygen content. When it reaches the nose level, you will be suffocating because you will have no oxygen for inhalation. And I have a document which shows that there have been more accidents reported because of suffocation of man-made refrigerants compared to ammonia. So ammonia, however, gets immediate newspaper publicity. Oh, there was a cold storage leakage, there was an ice plant. Nobody talks about accidents because of these man-made refrigerants. This is very important. Now you have understood why density is important. Now leakage losses. Another important point is density. If there is a 1 millimeter hole into a pipeline or some shaft seal is leaking, the molecular weight of ammonia is 17, whereas all other are having higher molecular weight. This means if the plant develops leaks of equal size, the higher density quantity will leak more. More quantity will be lost with higher density refrigerant compared to ammonia. Similarly, if you are purging the plant, more refrigerant will be lost, which is having higher density compared to ammonia. So these are the three important reasons why density plays an important role. Now let us talk the most important property, heat transfer rate or a conductivity. The disadvantage of heavier refrigerants is their heat transfer rate is lower during evaporation and condensation, because as a result of liquid film, the liquid does not evaporate so rapidly, and therefore the condensation or evaporation both these heat transfers are lower. The further the disadvantage, it has a lower thermal conductivity of these refrigerants compared to ammonia in the liquid phase. Now you will agree with me that none of the people who sell 404A, 410A plant, excuse me, I'm lot of people of these plants will be talking about or listening to my presentation, but they will not talk to you about this lower conductivity, lower heat transfer rates, higher density, etc. If you see, these are the values. Condensation outside the film, which is your condenser, shell and tube condenser, where your condensation is outside the tube, is 7,500 to 11,000, whereas all other refrigerants are 1,700, which is 1/6 or 1/8 of ammonia. The condensation inside the tube, which is your evaporative condenser, here also the rate of heat transfer is much higher with ammonia. Boiling outside the tube, this is a chiller, flooded chiller, ammonia, DX chiller, flooded chiller, where it is heat transfer is again nearly 2 times better compared to 404A, 134A refrigerant. And boiling inside the tube, which is your air coolers, evaporators, which are mounted in the cold rooms, where it is boiling inside the tube. Here also the heat transfer coefficients are much higher compared to other refrigerants. So these are the important properties you should remember when you are having that. As a summary, most of the thermal properties influencing heat transfer are favorable to ammonia. The specific heat of liquid is nearly 4 times better. Latent heat of vaporization is 6 times better. Liquid conductivity is 5.5 times better. Viscosity is less, so there are less pressure losses. Liquid density is less, as I mentioned, it is lighter than air. All these properties are very important properties when you decide which refrigerant to use. Ammonia is very important property, is lighter than air. Now, when your plant stops, many times your refrigerant condenses into a crankcase, and then we use electric heaters before starting the plant. If it is 404A, 410A, or 22, or other man-made refrigerant plant. In ammonia plant, we never supply any ammonia heaters because the ammonia floats on the oil. So your oil pump performance never deteriorates. The pump will always go on getting the oil. Whereas in man-made refrigerants, it is the mixture of refrigerant and oil which is sucked. And your oil pump performance will fail if you don't boil off the refrigerant by using crankcase heaters. Very important property. Piping design, oil miscibility. Now piping is important. HCFC 22, other HFC refrigerants, etc. use lubricating oils, and they are miscible oils. So they circulate along with the system, whereas ammonia and oil are virtually insoluble. Hence, recovering oil from various parts of ammonia is easier and requires different approach of oil management. Oil recovery problems are non-existent in ammonia at partial loads. Now, all of us know in HFC plants, HCFC plants, the problem is piping design. We have to be very careful in designing the piping to ensure that the velocities are maintained and the oil returns back to the compressor. Especially if you are using flooded systems, is very important. We have seen thousands, umpteens of problems where your crankcase oil is not received and it falls short of oil, there are breakdowns. So you are designing a pipeline. You have to provide double risers and complicated piping to ensure that oil always returns to the compressor in case of other refrigerants, whereas this problem is non-existent in ammonia plant. You can always drain the oil from wherever you want. So normally what I would suggest, select an oil separator which is a very, very efficient oil separator. If you select a very good oil separator, the oil will remain only into a closed loop of compressor and oil separator and will not go into the system, and you don't have to drain oil too much from various points into the system. The next important point is critical point. I will take about 5-10 minutes more. I hope I get that time. Critical temperature and critical pressure and density are important. All these temperatures, pressures, etc. are important, and critical density. We have already talked about density, but now look at critical temperature. Critical temperature of ammonia is the highest. So if you are using it for heat pump or for hot water generation, you get maximum recovery from ammonia plant compared to any other plant, compared to R22, R404A, 410A plants. The critical temperature of ammonia is much higher. Volume and mass flow rate, let us take 100 kilowatt capacity, 40 degrees condensing and minus 15 degrees evaporating temperature. The mass flow rate of ammonia is the lowest compared to all other refrigerants, and the volume flow rate is also lowest, which is very important. Ammonia refrigerant's mass flow rate is 1/7 that of 122 or 10.9.7 times lower than 404A. Only 1/7 liquid needs to be pumped. If you are using pump circulation system, your pump power for forced circulation system will be much, much lower in case of ammonia refrigerant. Looking at the other way, pipeline sizes. Look at this 200 kilowatt. I have just taken as a sample, evaporating temperature plus 5 degrees centigrade, and ammonia pipeline sizes. Ammonia 50 millimeter, discharge line 40 millimeter, liquid line 20 millimeter. Whereas all other refrigerant lines R22, 134A, 404A, 410A, you require a much bigger lines. Line sizes are bigger. So it is not only the cost of line size, but all your fittings, all your valves, and the most important is insulation cost is much more for other refrigerants. Or looking at the other way, if you take a constant size, pipeline size, 50 millimeter, what is the refrigeration capacity you get? R22, 134A, ammonia you get highest capacity, suction line 218 tons or kilowatt, discharge line 374 kilowatts, and liquid line, whereas all other refrigerants will deliver you lower capacity. Okay, we'll go a little faster. The tolerance to water. Ammonia systems are more tolerant to water compared to other systems. Lot of ammonia, buckets of waters have been removed. People say there is no water in our system, but even in developed countries like Europe, buckets of waters have been removed from ammonia, because ammonia system does not, it continues to work. It will consume more power, it will consume, it will get rest, but it will continue to work. It will not stop like HCFC or HFC, because little bit of moisture, immediately your expansion valves will get choked. So modest contamination of ammonia water system is advantageous because it prevents stress corrosion cracking. Now let us see the last property, pricing. Ammonia is 60 rupees a kg. This is the current prices. 134A, 450 rupees a kg. all other refrigerants are nearly 10 times more expensive compared to ammonia refrigerant. Ammonia smells are easily detectable, and this is actually an advantage. A lot of people will say it is a disadvantage, but 5 ppm ammonia leak can be detected. People can immediately repair it, whereas other refrigerants, they will not know that the gas is leaked out till such time your cooling effect is lost, and then your losses or replacement cost of refrigerant will be very high. So ammonia convinces with all the good efficiencies. We'll skip this slide, go to now disadvantages. What are the drawbacks? People will say toxicity, flammability, material compatibility, high discharge temperature, and oil miscibility. Let us talk about this ISHRAE standard 34.1 volume, toxicity and flammability. A indicates lower toxicity, B indicates higher toxicity. A1 is the lowest flammability, A3 is the highest flammability. So ammonia comes classified as a B2L refrigerant. We'll not go into more details of this slide. This will be available to you for study. Flammability classifications, as I told you, A1, A2, A3, no flammability, and the combustion energy. If you compare these with the flammability with diesel, petrol, methane, which are flammable, and we use these regularly in our cars or in our vehicles, but ammonia is very high, 15 to 30% is a explosive range. So it's much higher than our normal fuels. Ammonia is extremely hard to ignite. Its temperature is 650 above and breaks down at 450. So leaks are detectable even at 5 ppm. There is no reason that ammonia causes fire hazard. So flammability is not an issue at all. I haven't come across any plant where ammonia has caught fire. Ammonia concentration, LFL and HFL limits, lower flammability limit and higher flammability limit are 16% and 25%. It is significant to know that no ammonia refrigerant systems require use of any flame-proof control by any international standard. Our standard controls are usable. Very, very important point to remember. Now these are the safety classifications. We have already discussed about it, but you see flammability, A2L, B2L, 134A, they are all non-flammable refrigerants and low toxicity, whereas ammonia comes under B2L category. Toxicity. Toxicity, we will talk about TLV value, threshold limit value, time weighted average, etc. 400 ppm, you see 5 ppm ammonia is detectable by most of the people, but those who are refrigeration people, they will detect above 25 ppm because they are used to ammonia atmospheres. 100 ppm, no dangerous effect, only minor irritation. 400 to 700 ppm is, yes, leads to dryness, nose, mucus, irritation of eyes. 1700 ppm is cough, cramp, serious irritation, and 2000 ppm onwards can lead to death. But since below 25 ppm it is detectable, nobody will remain in that atmosphere unless one wants to commit a suicide. If you want to commit a suicide, remain in the plant room where there is a heavy leak of ammonia. So recommended minimum allowable concentration of ammonia is 2 milligrams per meter cube for 30 minutes, 1 milligram per meter cube for 24 hours, and 0.5 milligrams per meter cube for 1 year. ppm, to convert into milligram, you have to multiply by 0.7. ppm into 0.7 is milligram per meter cube. And so this is the unit of ppm, and I just want to impress that ammonia liquid leakage is much more dangerous than gas leakage. Gas leakage, gas will rise in the atmosphere, whereas liquid, if it falls on your skin, it will immediately give burns because it will penetrate right up to your bones. So liquid leakage is very dangerous, ammonia liquid leakage, and it being a latent heat is very high. It uh, creates very serious injuries. This is a vapor leakage, and the earlier slide is a liquid leakage. So vapor leakage is clouds, ammonia clouds we will be finding because it is immediately uh, goes into the atmosphere. The last point is ammonia discharge temperature. We have to use two-stage compressor or systems for ammonia, whereas R22, 404A, 410A, you can use single stage up to minus 25 degrees centigrade. This is because of the fact that ammonia index of compression, which we saw earlier, is 1.31. So the discharge temperatures of ammonia gas after compression are higher compared to other refrigerants. These are the discharge temperatures for the same compression ratio, plus 40 minus 20 degrees centigrade. The other R22 134A, others will have a discharge temperature much lower, 75 55, whereas ammonia is 145 degrees centigrade. This is, you can see as an advantage as a heat recovery, or if you use two-stage compressors, cascade systems, then this is not a problem because then the temperature comes down to 70 to 80 degrees centigrade after compression into high stage. Or you can use alternately mineral oils. Mineral oils, if you use, they can withstand 145 degrees centigrade temperatures. So this is what we discussed. Now the last point is material compatibility. Ammonia is not compatible with copper or copper bearing alloys, and therefore ammonia we always use open motor. A semi-hermetic or hermetic compressors have been, although developed, they have not become yet available in the market, and they use aluminum for winding of the motor because aluminum is acceptable to ammonia, copper is not acceptable to ammonia. The oil miscibility properties we saw already. The DX system, ammonia PAG and POG, PAG and POE oils have been available if you want to use ammonia in a direct expansion system. Coca-Cola, Pepsi, other plants, concrete cooling application, fertilizer plants, and supermarkets using ammonia CO2 cascades, liquefaction of gases, pharmaceutical plants, metallurgical industries, etc., etc., etc. So you can see ammonia can be used everywhere, including space and other travel. Space travel uses ammonia as a refrigerant because the system becomes very compact. Air conditioning of large complexes, skating rinks, etc., heat pumps, and marine refrigeration. So many other applications which have not been listed. The last slide is non-azeotropic liquid. Now, as we saw, toxicity is a characteristic, is a disadvantage. So to reduce toxicity of ammonia, people have started working by mixing refrigerants with other refrigerants, ammonia with propane, ammonia with 218, ammonia with 600. This is a condenser magazine by Monica Witt, which is a Euromon, and you will find that experiments have shown that compared to pure ammonia, some blends showed lower discharge temperatures, lower compression ratios, better refrigeration capacity, and better solubility with oil, and reduces toxicity to a great extent. I think I have taken 10-15 minutes more, but thank you very much for giving me this time. I wanted to discuss ammonia properties in detail, and I hope, as I told you, I'll be able to answer all your questions on mail. Send me a mail, give a mail to ISHRAE. They compile all the questions and they send me a mail where I am able to reply all questions raised by you. Thank you very much. I once again thank you for patient listening. And our next session will be various ammonia systems, single stage, two stage, cascade, etc., etc., etc. We will discuss that in as a presentation number 3. Thank you very much. Goodbye.
Thank you
Please
so much,
take
sir.
over.
Thank you so much, sir. For the benefit of all the participants, Mr. Ramesh Paranjpey has been delivering this lecture as a volunteer. You can understand that it's just out of passion, no monetary advantages. This is what the volunteer of ISHRAE does for ISHRAE. And it's supporting the mission of ISHRAE to disseminate knowledge amongst all the ISHRAE members and the industry. I'm really thankful to you, Mr. Ramesh, on behalf of ISHRAE headquarters, ISHRAE leadership. I would like to thank you personally also. And without participants, we could not have a successful webinar. All the participants have been staying till the end. So that shows how important and how informative the session was. So we are all looking forward to meet you for the third session next Friday, that is 17th July, on various refrigeration systems, their applications, advantages and drawbacks. And without the support of HU Secretariat for the technical support that they are given, such kind of webinars are really difficult to broadcast. So I would like to thank the HQ Secretariat, especially Mr. Ravi Kumar, for extensive help and support on the technical front. Thank you all of you. See you next Friday. Good night.
Thank you very much. I'm sure now all of you have realized both positive and negative points of ammonia, and positive points outweigh substantially those negative points. Thank you very much. Bye.
Yes. Thank you so much, sir. Thank you. See you next Friday, sir. Thank you. Thank you all of you.
Thank you, sir. So let's close it now. Thank you very much.
Yes.
Bye.